Next example is a Wheatstone bridge. This is another example of a circuit, a resistor arrangement which is neither parallel nor in series. So as a result, in the general case, you have to use the usual circuit techniques to solve this problem of finding the equivalent resistance problem. But there is a special case. There's no symmetry in here, but there's a special situation where, in that case, we can solve the problem with a very simple trick, right? That special case is the case when in these four all-side branches, the resistance ratios satisfy that relationship, that is R1 divided by R2 is equal to R3 divided by R4. Right? Ratio of this resistance to that resistance is equal to the ratio of that resistance to that resistance. If that's the case, then, well, it's not a symmetry, but we can say a similar kind of a thing like in the previous problem. Right? Let's call these 2 points as C and D. So we will see what happens in that case. What I'm going to say is that the points C and D have the same potential, and so therefore there is no current flowing on this fifth resistor in here, no current on that branch, and so therefore the value of the resistance of that branch is not important. So let me erase these things in here, and I'm just going to write it down like that. So I'm going to assume, right, suppose R5 is not there, right? Suppose that this fifth resistor is not connected, so there's infinite resistance in here, so C and D are not connected. Okay, so in that case, what happens is this: I can basically think about this upper branch and the lower branch separately. Okay, I notice that because of this resistance ratio being the same, I can say the same thing, say this thing: potential drop in AC is equal to the half of the potential drop of CB. Okay, so that means I divide the potential difference on AB into 3. One part falls on CA and one part falls on CB. The reason is that the potential drops on these resistors should be proportional to the resistances, because the same current is flowing on them. So since the resistances have the 1:2 ratio, potential drops on these two branches should also have the 1:2 ratio, and so therefore the potential of C somehow should divide that potential difference into 3 parts, and 1 part will be on AC and 2 parts will be on CB. Okay. So, of course, since the ratio is the same, I can also say the same thing for the AD and DB branches. And so, therefore, the potential of point C is the same thing as the potential of point B. And again, in that case, no current will flow. Current will flow if R5 is connected, which means the value of R5 is not important at all. So I can change the value of R5. So that strange value, that's the significance of that one. So it doesn't matter if this was 30 ohms or infinite ohms or 0 ohms. For the whole circuit, I'm going to get the same solution independent of what that value is. And so therefore, this gives us 2 alternative techniques for solving the problem. I can replace this R5 with infinity. So that's the situation where I replace R5 with infinite ohms. In that case, I have this arrangement of resistors. So we have an upper branch which has a resistance of 3 ohms and a lower branch which has a resistance of 6 ohms. So as a result, these two have a resistance of 2 ohms. Therefore, the equivalent resistance is 2 ohms. Or again, just like in the same the previous problem, this is an alternative solution. I can replace R5 with 0 ohms. That means I can connect these 2 points with a wire, in which case, right, I have this kind of an arrangement. R1 is in here and R3 is in here, and R2 is in here, and R4 is in here. So that's R1, R3, that's R2, R4. Okay, for this part I need to use some calculation in here. I need to compute the sum of the reciprocals. So I have 1/1 plus 1/2. That's going to give me 3/2. So this part has a resistance of 2/3 ohms. And for that part, I don't want to do the calculation. I know that the resistance ratios are 2, so therefore I'm going to get 4/3 ohms in here. And so therefore the equivalent resistance is the sum of these two, which is R prime plus R double prime, which is 2 ohms. So again, it's the same answer, but found with an alternative way. Wheatstone bridges can be used for building some ohm meters. So we have a situation like that. Let me draw the picture again. Okay, so we have let me use an ampere meter in here. All right, so we have R1 and R3 are, let's say, are known resistances. I have an unknown resistance in here. This is R2. I don't know what it is. And R4 is a potentiometer, that is a resistor with an adjustable resistance. It doesn't matter what that fifth resistance is, as we know, but there's a device in here that measures the current that flows from that branch. Right? What we do is we just connect these A and B points. This is A, this is B, to a battery. So what we do is we just adjust the resistance R4 until no current passes on that branch. So R4 is adjusted until no current passes over R5. R4 is adjusted until no current passes over R5. And in that case, of course, this ratio should be satisfied. R1 divided by R2 is equal to R3 divided by R4. So as a result, we can express R2 in terms of other quantities. So that's R1 over R3 times R4, right? So that's one way of measuring the resistance of an unknown resistor.